Hi, welcome back to Blockchain Fundamentals with Bill Laboon. Today we're going to discuss other forms of proof of work besides the Bitcoin SHA-256 hash pre-image puzzle that we've discussed in the past. So before we dive into the details of the variations, I want to bring you back to when we first discussed the hash puzzle properties when we talked about proof of work earlier. So first, we need to have some calculation that is difficult to compute. We can't, if anyone is able to very easily create a block with the correct proof of work, then we don't really have a good proof of work system. It should be parameterizable. That is, we should be able to adjust the cost that it takes in terms of computation in order to come up with an answer. Otherwise, as more mining hash power or whatever the equivalent in computing power is besides hash power comes online, then we won't be able to adjust the network, and we would then see differentiation in block time or other issues. Conversely, it should be difficult to compute, but trivial to verify. That is, anyone can look at this and ensure that it is the correct result. So, a good analogy for this is a Sudoku puzzle. It's a very difficult to solve one, but anybody can look at the Sudoku and very quickly determine that it has been solved correctly. And finally, it generally should be a progress-free or memoryless process. There shouldn't be a way to store this information to use for later. We should be able to basically start afresh each time we're trying to solve it. So, if you remember, Bitcoin's puzzle is, as I mentioned earlier, a partial hash pre-image puzzle. So the goal is to find a value, if we take some hash function h of the block in some nonce, and make sure that it is less than the target, which is why if you look at Bitcoin block hashes, you'll see they start with lots of zeros. They're trying to create something that's lower than a target so that it'll start with a lot of zeros, as it's very small. So could we modify this in any way while still maintaining these properties? That it's difficult to compute, trivial to verify, and has a parameterizable cost. So of course, from a trivial perspective, of course, so instead of trying to create a very small target, perhaps we try to create a very large target, or we try to calculate the number of zeros or ones in binary representation, or we XOR it against a value while still getting the basic idea of a hash pre-image. So we can make these slight variations, but then the question is, why would we want to? What benefit does it give us really to try to create something larger than a target value instead of smaller than a target value? Well, so there's no real benefit to this, but would there be benefits to more extreme variations of this, to larger changes to this basic concept? And of course, there are a lot of reasons that we might want to do that. There's not really much of a reason to just flip the Bitcoin puzzle around so that it's higher values instead of smaller values. But there are some issues with Bitcoin that we can see if we can fix them by changing our proof of work algorithm. So the first, and this is something that you hear people talking about quite often, is most Bitcoin users do not mine. So even though in Satoshi's original white paper, he talked about one CPU, one vote, it turns out that GPUs and later FPGAs and ASICs were much more efficient, dramatically more efficient, orders of magnitude more efficient at mining, at solving these SHA-256 puzzles. So in order to mine profitably, you really need specialized hardware. So there are also a lot of economies of scale. So for instance, if you are a large mining corporation, then you may be able to have access to cheaper electricity. You can buy things in bulk. You can have people that are paid to determine the most efficient airflow and what is the correct amount of wattage to send and turn things off when it's unprofitable. So generally now we have mining like groups or corporations. So is this good or bad? And there are, you can definitely argue in some ways that it is a good thing, but many people see this as a problem. It's not really decentralizing the network, because you have certain groups, perhaps that own a large percentage of the mining power. And so one way to solve this is to sort of fight against ASICs. So we have this concept of ASIC resistant proof of work. So here we're going to disincentivize the use of custom-built hardware, which means that in essence, that ordinary users with ordinary computers, or perhaps those with GPU setups as opposed to more specialized ASICs, will be able to mine on more or less an equal footing with those who own specialized hardware. Now, this can never be perfect. Generally, no matter what mining algorithm or what proof of work algorithm you use, some hardware is going to be better than others, right? Even if I try to mine, just to take an odd absurdum example, on my old Commodore 64, that's going to be much less efficient than a modern server that I could get off some cloud service or whatever. Right? For a variety of reasons, it's going to be less efficient. So we can't say that any hardware is going to be exactly equal, and even hardware that might be of the same time period and same general structure may have like slight differences in the system that might make it easier to actually program a particular algorithm, right? To write a program to do a particular algorithm. Maybe it has certain instructions that make XORs or bit shifts or whatever faster. Okay, so there will always be an incentive to make ASICs. It should always be possible to make something that really is an application-specific integrated circuit, right? Some hardware that is specifically meant for this whatever algorithm we're using. But can we narrow that gap? Can we make it so that perhaps creating specialized hardware might give you a 1% bump instead of in efficiency, as opposed to orders of magnitude, where it then is not worth it to develop these ASICs. They take quite a while to actually produce, right? From designing to sending them to the chip fab, etc. It takes a while. So can we narrow this gap? So there are a variety of ways we can do this. So I mentioned, actually, I think in the last lecture, about how Monero will change, and a few other systems will actually modify their algorithm every few months. And so it just doesn't make sense to produce the hardware to mine on it, because it will be obsolete very quickly. But if we want to maintain the same, so that's sort of a trivial way of doing this, but if we want to maintain the same proof of work algorithm, one other thing we can do is try to make a memory hard and memory bound algorithm. So one of the reasons for this is because while making a chip that is specialized for an algorithm is something that's straightforward, may be too strong of a word, but relatively straightforward, memory as a limiting factor is going to be very similar across all systems. Anyone who uses memory is going to be stuck on a regular computer or an ASIC. They're going to be bound by the interaction with that memory. So I'm not saying there aren't any tricks we can use to speed up access to it, but again, it's going to be much, much less than the benefits you can get from specialized hardware performing calculations, like a CPU or CPU equivalent. So what do I mean by memory hard and memory bound? So a puzzle that requires a lot of memory, and this might be in addition to CPU power or without a lot of CPU power, but just if it requires a lot of memory in order to calculate, we say that it's memory hard. That so for instance, like a Sudoku, sorry, algorithm does not, like the actual memory used for it, it's probably not a lot if there's not that much state involved. But if you're doing a pathfinding algorithm amongst a million by million array, and if you want to find an optimal path amongst those, you're going to need to load a lot of data to understand, in this giant array in order to actually calculate it. So that doesn't mean it's impossible to do. You can always just load what's around you, but there's still going to be a lot of memory access as you do this. So if the time to access memory is the limiting factor, that is, it's the bottleneck to computation, then the puzzle is memory bound. The accessing memory is really the aspect of the algorithm that really causes us to limit what the time is. So something could be memory hard, that requires a lot of memory, but it turns out that the CPU usage is going to be the limiting factor. So in that case, something is memory hard but not memory bound. You may have something where accessing an algorithm where accessing the memory is the limiting factor, but it doesn't really require a lot of memory. So that would be something that's memory bound but not memory hard. You may have some systems that, such as SHA-256, that are not memory hard nor are they memory bound. But ideally, we want our puzzles, if we're trying to be ASIC resistant, to be memory hard and memory bound. So in this, because the time is bound by the memory storage and not the processor design, that's the limiting factor. So increasing the speed of the processor or designing it to be for our particular algorithm is not going to help us. This is harder to parallelize without just buying more memory, in which case what's the point of having this specialized hardware when really you can just buy more memory for your computer. Okay. So as I mentioned, SHA-256 is neither memory hard nor memory bound, which is one of the reasons why it's extremely simple to make ASICs that are designed specifically for it. So I'm not saying that any of these other algorithms I'm going to use or refer to don't have ASICs designed for them. So it's why I say ASIC resistant, not ASIC proof. If there is enough money to be had, right, enough profits, what you'll see is that even the smaller improvements that you get from an ASIC then become profitable for people to create. And in this capitalist world we live in, if it's profitable to create, probably someone will do it. So that being said, let's dive into one of these algorithms. So one of the first altcoins, Litecoin, actually uses this algorithm. It's called scrypt. So to me, I always want to say script when I look at it, but it's actually pronounced scrypt. This was originally designed for hashing passwords, so it's was not made specifically for Litecoin, but rather it was repurposed to be used as the Litecoin hashing algorithm. And there's the same basic idea of producing, given some data in a block, we want to produce a hash, like it was a partial hash pre-image puzzle, but we want to make sure that this has a reliance on memory. So I'm going to walk through, and I've got some pseudocode for how scrypt works here. So for scrypt, we're going to create this buffer right? That is basically an iterated SHA-256. Okay, so we create this large size of the buffer given with a seed, and for the size of the buffer, so this is of non-trivial size, we are going to get a value, take its SHA-256 value, put that in the next slot in the buffer, take that SHA-256 value, put that slot in the buffer, and then jump around to a different place in modify and jump around in that array until we get to the end and return the value that has been created from all of that. So again, think of like a Sudoku puzzle where one block really is dependent on the next one, except we're using SHA-256 and doing this in a very linear order. So just SHA-256 of this, and then take that value, the SHA-256 of that. So now, in order to get a result, we're going to need to be accessing this memory. Okay? So this is something that you can do by recomputing all the values in the buffer every time you want to go through, but this becomes problematic as the size gets beyond non-trivial values. Yep. So what this essentially means is that if on average we're going to have to calculate, if we don't store any memory, however big the size is, half of that in SHA-256 hashes. Okay. So if you are familiar with your big O notation here, if we use a buffer, then we only have to calculate 2 times size computations, which is big O of n. Whereas if we don't use a buffer, we have big O of n squared. So n squared is going to grow much, much, much more quickly than O of n. So it is possible to do this without using memory, but it makes things a lot easier. But as I mentioned, this has only helped to make this resistant to ASICs. There are scrypt ASICs out there, and so there is a problem with this, right? Because as Litecoin increased in value, it then became worthwhile for people to create ASICs for Litecoin mining. So there are other algorithms we could use that are memory dependent, that are not that are also memory bound. So one is Cuckoo cycles, and I think this is pretty interesting. It's a graph theoretical hashing algorithm. So instead, quote unquote, hashing algorithm, it's used for eternity blockchain proof of work, as well as a variation of this, a slight variation used in Grin. If you've heard of Grin cryptocurrency, for its proof of work, it uses some variants on this. And the basic idea here is, given the data in a block, okay, convert it into this bipartite graph. So a bipartite graph just means it is a graph like this, where the nodes are grouped into 2. Right? And anything from the first group can only go to the second group, and anything from the second group can only go to the first group. So then we want to find a cycle, a loop in here. So a very simple cycle here would be 1A to 1B, 1B to 3A, 3A to 3B, 3B back to 1A. So we have a 4-element cycle here. Okay, so we've gone through 4 nodes. So how could we use this for proof of work? So given some data, we're going to send it through a hash function, then interpret that output as edges between the nodes. So we have some very large number of nodes that we're going to have to store in memory, as well as the edges where they are, and then look for a cycle of a specific length. So for Grin, for instance, we're looking for a 42-element cycle. So here, once again, if when we have these bipartite graphs are going to be very huge, like millions of edges, millions of nodes, and so storing them in memory is really the most efficient way to do this. And if we're depending on memory, we are in some sense ASIC resistant. So again, resistant, not ASIC proof. So is this a good puzzle? So yes, especially as we get a large number of nodes. It's parameterizable because there are a lot of ways to adjust the difficulty here. We can increase the number of nodes or the size of the cycle you need to find. We can add restrictions to which edges are valid. Like we could say in all sorts of different variations. Like if it's any edge that's modulo that's even, so let's say has to go any node that's even has to go to an odd node and vice versa. Okay, so we just made it difficult by adding restrictions to which edges that we can follow. However, given a cycle, it's trivial to verify. And it's progress free. You really just need to try different possibilities. You never know if you're going down the right path or not. So this is another variation, like I said, of an ASIC resistant puzzle. There are others out there, but these two examples hopefully give you a chance to see how we can be ASIC resistant just by ensuring that we are memory bound and memory hard. So let's go a little bit further afield. Is mining wasteful? So we're spending a lot of energy here, right? A lot of electricity. I've already mentioned Bitcoin uses more electricity right now than Switzerland does. But what are we doing with that? We're solving partial hash pre-image puzzles. We're finding cycles and graphs that we make up. So couldn't we use all of that computational power for something good? We hear about, there are supercomputers that help predict the weather or cure cancer or look for signals from aliens. Couldn't we do something like that with all of this? Or maybe can we get rid of proof of work? But we'll talk about that next lecture. But now let's say that we have to do some sort of proof of work. Let's make that assumption for now. Like I said, that's an assumption that we will take away and look at in the next lecture. But for now, let's say we have to mine. So couldn't we do something with that? Right? There have been a lot of distributed computing projects, right? And so there has been some cheating in all of these, but it's generally detectable. It hasn't occurred to a great extent. They're still running. Perhaps some great examples here, SETI at home, so looking for signals from aliens, or folding at home, looking at protein folding to help look for different cures and understand how proteins fold, helping the medical industry. Looking for very large prime numbers, right? So with the Great Internet Mersenne Prime Search, GIMPs. But it turns out that none of these are good fits for cryptocurrency. There are a lot of challenges to doing what we call proof of useful work, to creating a puzzle that is useful, that people want to have solved, but also can be used as the basis for proof of work. So there are a few challenges here. First, we need to make sure it's an equiprobable solution space. That is, we need to make sure there's no way for anyone to go and cherry pick data. They can't go and just look for the easiest proteins to fold, right? Or the whatever. Make sure that they're looking at a star instead of looking just randomly into space. In other words, it should be puzzle friendly. We need an inexhaustible puzzle space. This doesn't technically mean infinite, but we do need to make sure that we're not bounded by the data that's out there. So we can't have with the SETI, for instance, if a radio telescope went offline. Let's say they're getting data from the Arecibo radio telescope and it goes offline. Does that mean that our proof of work cannot proceed? Okay. So generally, this is going to need to be algorithmically generated. Otherwise, we've got a centralized point that's providing this data, which means it can be gamed or turned off. Right? So generally, with a cryptocurrency, with blockchain in general, we want to have something that's decentralized as much as possible, and data that's coming from a specific place or coming from specific people is definitely not decentralized. Right? Even if you have a decentralized group, there's going to It's certainly not going to be as centralized, as decentralized as something that can be algorithmically generated by the chain and the nodes themselves. So just looking at the specific examples here, SETI at home, well, there's definitely a lack of equiprobable solution space. We know that if you're looking, not at a particular star, then you're much less likely to find any sort of alien signal or something that would be valuable. It's a lack of inexhaustible puzzle space. It's going to be hard to verify that you actually have found a signal, right? There are certainly some checks, but there's all sorts of different ways that this would have to be checked by someone. And this data is not really algorithmically generated. We know we're getting it from space. It means we're getting it at least from a radio telescope or someone who claims to be a radio telescope. So all sorts of problems with using this as proof of work. Folding at home, a lot of the same problems that we have with SETI at home. We're getting the data from some specific places. The Great Internet Mersenne Prime Search. So this actually looks interesting at first. So we have modulo some trivialities on where we already know that Mersenne primes have been found. So Mersenne primes are just a prime of the form 2 to the n minus 1. The puzzle space has actually been proven to be inexhaustible. So we know there are an infinite number of Mersenne primes. And data can obviously be algorithmically generated. Like this is just people trying out different numbers. But the problem is one Mersenne prime on average is found per year. So here we seem to have run into a wall. We don't want to have, I think it's okay to have variable time, but I think 1 year between blocks might be a little much. But we can take this idea and actually and run with it. And actually one cryptocurrency did called Primecoin. So Primecoin was the first, and as far as I can tell, the only proof of useful work coin out there that actually got any traction. Not that it got that much traction, but I think it's an interesting idea. And it looks for Cunningham chains of primes, which I'll discuss what those are in a second. And I don't want to disparage any mathematicians out there, but the question then becomes, how useful is this work, looking for chains of prime numbers? And I think, again, you can certainly, make an argument that this could be useful and interesting. However, it's not exactly the same as calculating protein folding. So just so you understand what a Cunningham chain is, it's a sequence of k prime numbers, so p sub 1, p sub 2, up to p sub n, such that p sub I equals 2 p sub I minus 1 plus 1 for each number. That is, if you take a prime number, p sub I, double it and add 1, and check to see if it's a prime, however many times you can keep doing that doubling and adding 1, and the resulting number still being prime, that's a Cunningham chain of length k. So, for instance, 2 is a prime number. If we double it and add 1, we get 5. 5 is a prime number. Double it and add 1 and get 11. Prime. Double that and add 1, we get 23. Prime. Double that, add 1, we get 47. Prime. Double that and add 1, we get 95. 95 is divisible by 5, and so it is not prime. So here we can see, starting at prime 2, we have a Cunningham chain of length k equals 5. So it's conjectured, but not proven, that there are Cunningham chains of length k for any k. We don't know that, but not proven. But people have done a lot of this. Primecoin has been running for a while, and the longest known, as of the writing of the slide, was k equals 19. So there are a lot of these. This is something, this is useful work, and we actually can go through it. So how we can do this is get the hash of the previous block, take the first m bits, and we consider valid a chain of length k or greater. So we set this k. The first prime in the chain is an n-bit prime. All right, so we're getting some size. Right, and then the first prime in the chain has the same m leading bits as x. Okay, So we're looking for a specific kind. And then we can adjust n and k to automatically adjust the puzzle difficulty. So if we modify k, this is going to change the difficulty exponentially, and if we do by n, polynomially. So we actually can make smaller adjustments and larger adjustments. So this is one interesting chain, and it is out there, and you can look into Primecoin if you're interested in one form of proof of useful work. So Golem is not exactly a cryptocurrency per se. It runs on Ethereum, but it is sort of a variation on this proof of useful work that I think is interesting to look into a little bit. So the idea is you can rent out computing power of your own computer and perform large-scale computing tasks. And these the initial task is for rendering of 3D video, but in theory it can be used for other large-scale distributed computing tasks as well. And then you are rewarded by doing this. So how do we verify? So different nodes given the same data should return the same result. So this can be checked, right? If I give the same data to multiple nodes and two of them give me the correct result, quote unquote correct, we have no way on chain of knowing this, and one gives me an incorrect result, well, I can look at the incorrect result and not give them a reward. So there are ways of checking this out, right? And then if we have a large enough group and we randomize who gets these the same chunks to check on each other, then we actually can get some good results. However, right now there is a centralized payment mechanism and verification. It hasn't been entirely decentralized yet, but I think this is a very interesting variation on proof of useful work. So it does allow you to, it has sort of one step removed. It's not using the useful work as part of the block production mechanism, but it does allow you to use your computing power and get rewarded for it. So remember I had mentioned about with memory and storage in general. So this is not just memory per se. Is not going to use up as much energy, and it's also going to store things on, but it's also much more commodified. It's hard to make storage that is really focused just for cryptocurrency mining. So there are a few blockchain systems that use proof of storage. So this also has the benefit of being able to actually use that storage for interesting and useful things. So just like IPFS, we can store that data and retrieve it later. So proof of storage, we're going to represent some file or collection of data, just a really large Merkle tree, and then all the participants agree on a Merkle root, and the miners are going to store some subset of data associated with that key, and then they can be asked for it, and if they successfully produce it, then they can get rewards. So there are a few different systems that use this or variations of it, such as Filecoin or storage. Not all exactly the same idea here, but the same basic concept is that you're rewarded for storing things. So this is another form of proof of useful work, right? Because storing this data, if it's not just random data, if it's something people actually want, that's something useful. However, overall, is using proof of useful work a mirage? So there are a lot of technical drawbacks. I mean, there are benefits to doing this in such a decentralized way, especially data storage, but there aren't a lot of benefits for using it directly for block production. Okay? So there aren't a lot of computations that meet all of the requirements that we need for true proof of work. So obviously these variations where we get these such as Golem or using proof of storage to store useful documents, those were not directly always generating blocks from them, but they are something that hasn't quite taken off yet. Now, that doesn't mean that they won't, and certainly I see a lot of promise in a lot of these projects. However, it's just speaking personally and subjectively there. However, it's not something that has really taken off much yet. And in fact, there are some that argue if you actually want to have value behind these, if you actually want to use something as money, then it needs to be generally not useful otherwise. You can't actually use it for anything. So you can see the Bitcoin standard for that argument. Now, that doesn't mean, though, that the tokens would be worthless, right? That if you're using them for something that's useful, or you're getting other kinds of tokens, then it may actually be worth your while to do this mining and work, even if it's not technically money. So this is something interesting, and I'll be very curious to see where it goes in the future. All right, so the last issue with Bitcoin that I want to discuss with Bitcoin mining and a solution that can be used with by changing the proof of work to help fix it is pools. So a mining pool, remember, we discussed these earlier. We have a group of miners. They're not always, we can have a lot of different miners from all over the world. They're all part of one group and that are acting as a single entity. And there are some benefits to being part of a pool. We talked about reducing variation in your payouts and things like that. However, pools might lead to centralization, right? So this is a problem when not everybody is mining on their own. They're a target for malicious actors, right? That's where the money is. That's where people might be tempted to attack. If you're not an admin on a pool, but you're mining, then you aren't running a full node. And we want people to run full nodes because that helps everyone keep an eye on the system and make sure that all of the transactions are valid. These pools are not part of Satoshi's vision. If you read Satoshi's white paper, there was no talk of pools. So it turns out that mining pools are really only possible because it's very easy to prove that you're working to find valid blocks even if you don't find one. And it's impossible to modify the recipient. So you can't change, after you find a block, you can't change who the payout is going to go to. And there are some attacks that are possible with pools. Like if you want to harm a pool, but you don't care about the damage to yourself, you could always submit shares, so you'll get some value out of it, but when you find a valid block, you ignore it. So you don't submit it. So this is not, as far as I know, seen much or at all, but theoretically it is a valid attack that you could do, especially if you're interested in causing damage to another pool, or if you're an attacker who is not so much concerned about the cost to yourself, but more about damaging the other pool. This pool might have a lot of hash power, but never, and is doing a lot of paying out, but is not actually ever finding blocks, or at least finding them much less because you're hiding them when you do this. So there is this idea of non-outsourceable puzzles, which are puzzles which disincentivize pools. So an easy solution for this, if you have all miners, if you're required to know the private key of the address that you're sending to, well, you might trust some of your friends to do this, but you're certain, or your family, but you're not going to trust anyone in the world. So this there are some of these non-outsourceable puzzles that people have written about in the literature, but as far as I know, there's been no real implementation of this. There's been a lot of talk, or I shouldn't say a lot of talk, there's been some talk of it, but as far as I know, no one has actually implemented it, although it certainly is possible. So these are just some of the variations of proof of work systems, especially in the early days of 2011 through 2013. There were a lot of different proof of work systems that were tried. However, we don't see this as much now anymore, looking in the last few years. And so I'm going to talk about one of the more popular block production and mechanisms. So instead of proof of work, we'll talk about proof of stake. So that will be in the next lecture, and I hope to see you all then.